lab this week is very so let's talk about lab. Monday lab people, you have nothing. Although you are welcome, if you want to get things done early, the lab is going to be due next week, Wednesday. I just figured it would be the easiest. If you want to get started on the lab before lab, you're welcome to do that. It's pretty short, but it's all homebrew stuff. It's all, you're going to be sketching out what we drew in lecture. Actually, and for the lab introduction, I'm literally just going to walk through the lecture notes because it's really, I'm testing, are you seeing what I'm seeing or what I'm intending to convey to you with plate tectonics? So, you know, we covered a little bit about South America and that kind of stuff, and now you're going to do the same thing for India. Basically, you're going to replicate some of the drawings and stuff we made of oh, we haven't even gotten to that point yet. Oh my goodness gracious. We just finished metamorphic rocks in this class. So, and we just talked about the introduction. I'm sorry. Let's move this up here. Let me show you. Got you mixed up with another class. I'm so sorry. And I am authentically sorry when that happens. That's definitely not my intent. So yeah, so this week's lab will be due on Wednesday next week because Monday lab people won't be able to do it until next week, and Tuesday lab people are doing it today. However, like I said, if you're following along with the plate tectonic stuff I'm going to lecture on today, and you take all these notes, you will have the answers. You have the answers. You've just got to stick them in the right spots in the lab and do the drawings I drew, okay? So yeah, you definitely can start that way before your lab time. So can you hear me when I'm standing like this? Because I know this is a directional mic and there's sometimes a question. Awesome, yes. Thank you, Jamil, thank you, Morgan, thank you, Malachi. So we covered a little bit of the history of plate tectonics. Let's go a little bit more into plate tectonics itself. Yeah. Okay. So,
I gotta hang up, right?
Oops, somebody's mic's on who may not want it to be because I don't think that was an answer to me. And the previous lecture notes are posted, just as a heads up. So you should be able to find that straightforwardly sort of a thing. So let's talk more about plate tectonics. Okay, I'm actually going to grab one of my other classes notes. So we can get on the same page and I make sure that I'm covering what I want to cover. So basic idea, plate tectonics. We have three major plate boundary types. Does anyone know what the three major plate boundary types are? We did this? I knew we did this. Damn it. Thank you. I didn't see this. Okay, so we went through South America. I was like, why are we so far behind this other class? I thought we were right on target. I'm sorry. So we're right here. We just covered transform plate boundaries, right? Yes, thank you. And we find transform plate boundaries, for example, in California, in the San Andreas fault system. And I know that we've gone through a little bit about transform plates. I do want to draw you a section, have a conversation about that. So transform plate boundary, I should put the date up here to 16/2021. Transform plate boundary, the revenge continued. Okay. So we're going to start with the cross section. Originally, I don't usually draw the cross section, but it's just helpful visually to understand what's really going on. And if, like, where were we? I was like, where were we? Yeah. It was a long weekend. Anyways, so cross section. I wasn't originally going to draw a cross section, but it's good in order to get a little bit of contrast with the other plate boundary types. So I'm just going to go ahead. This is the lithosphere. This is the asthenosphere. And what does this brown portion up here represent in the lithosphere? Crust. Excellent. This is why we take notes. Exactly, Robert. And actually in regular class, I have like a printout outline of notes, so I really can't get lost because I see what's already been filled out before. But there you go. So that represents crust. And down here, this is mantle. And we have that mantle penetrating up into the lithosphere. Part of this lithosphere is considered part of the mantle. There is overlap between these layers, but this is a relatively solid, rigid layer that can move. So, if we were going to draw a transform in cross section, this is what a transform would look like. So a transform is basically just a crack in the lithosphere where sliding occurs. Okay. Now an important key is that transform fault boundaries fault boundaries are common near other types of boundaries. And we often find them where multiple boundaries meet. But we can also find them on their own. So where, for example, the San Andreas fault system is a legit just fault system that is a transform plate boundary just kind of chilling all by itself. It's occurring because the North American plate is moving one direction and the Pacific plate is moving another direction. And as those two slide past each other, now we have a transform plate boundary. But there's even more transform fault boundaries around. So an example is the mid-ocean ridge system. Now this is actually super confusing in your book. There's diagrams in some versions of your book that it really makes it look like a divergent and a divergent and a transform plate boundary are actually like the same thing, simply because they put them in the same diagram. It's really bad what we would say iconography, because it's not clear that, you know, transform plate boundaries are their own thing and function differently and have a cross section that looks something like this. So if we have the mid-ocean ridge system, this is our divergent plate boundary, and this is a map view. So this is looking down. So this is not a slice in the earth like this one is. This is if you slice downward. We're standing on the surface, and you like you could take a chunky chunk out of the earth and just stand back, and you could look at that surface. Okay. Down here, this isn't like this. This is like if you were looking at a map from up above. So let's go with green. Green is a good different color. So the transforms are like this. Okay, they basically hash all along the divergent plate boundary. And the reason that that's happening is that here we have seafloor spreading. So as that seafloor spreads apart, there's going to be a lot of uneven stresses. In other words, directional forces. So there's going to be some tension developing. So that's a pull apart force. There might be some compression, push together force. And there's going to be a lot of shear, sliding across each other forces. So, so because of that, because of all these uneven forces, we basically end up with tiny tears all up and down along this mid-ocean ridge system that are these transform fault boundaries. And what we also, I mean, basically it ends up looking like the whole Earth. If you could take away the ocean and you just drew along the divergent and transforms, it would almost look like baseball. It would look like a baseball where you have like the seam that runs around the baseball, and that would be the divergent plate boundary. And then the transform would be like the stitching. And some people are like, oh, that actually makes sense. And then other people are like, Dr. Evie, I don't do baseball. But I do baseball, and I think that's a pretty good example if you're used to baseball. So. Any questions about this before we keep moving? Hearing none, I'm going to assume that all things are hunky-dory in the universe of the other side of the screen. We're going to go over here, and actually we're going to use this whole sheet because Dr. Eby learns a few things every time she does something, and she ran out of room last time she tried to do this. So we're going to do a big review. It would be great if I could spell review correctly. Review of plate tectonic features. Let's zoom this. I'm going to zoom this out as far as it's going to go. Okay. And so some of the features that we'll be worried about include island arcs, continental arcs, mountain belts, mid-ocean ridges, trenches, and earthquakes. Okay, so these are all features associated with at least one of the three major plate boundary types, which are divergent, convergent, and transform. So let me go ahead and divide this up. And if you're taking the notes, you go ahead and divide yours up too. And I want to make clear from the outset that this chart is focused on causal relationships. So it's not like you'll never see a mountain belt near a transform plate belt boundary, but transform plate boundaries don't cause mountain belts, for example. You might be like, why are we making this so big? It's because we're going to also be putting in some notes, clarifications, that sort of thing. All right. So we've got our little chart right here. Let's get moving. So island arcs. Which kind of plate boundary causes island arcs? Look back through your notes. What kind of plate boundary causes island arcs? Oh, this focusing on causal relationships. So this whole chart is focusing on causal relationships. In other words, which kinds of plate boundaries cause these features? Because, for example, you can have transform plate boundaries near and mid-ocean ridge, but the transform plate boundary isn't causing the mid-ocean ridge. So very often you'll see an overlap where maybe there's a transform near a continental arc, but that's not the plate boundary that's causing the continental arc. So island arcs, what kind of plate boundary makes island arcs? Good question, Hannah. Convergent, excellent, Stephen. Excellent, best answer, Robert. So divergent and transform do not cause island arcs, but convergent do, and that is an oceanic convergence. So we're going to say yes. Now, what about continental arcs? What causes or doesn't cause continental arcs? Continental oceanic convergence. Excellent, excellent, Stephen, excellent, Robert. You're doing great. Divergent doesn't, and transform doesn't, but now we have oceanic continental convergence. So we would definitely say yes, some types do. What about mountain belts? This is actually a little bit harder because it wasn't totally clear in the notes so far. What kind definitely does? Excellent. So the biggest mountains are caused by the huge mountains, and by which we mean, like, for example, the Himalayas. At some point I will learn how to spell Himalayas. So I'm just gonna, because I am that person, I am actually going to even underline this in blue, Himalayas. Okay, so the huge mountains like Himalayas are, as Robert pointed out, continental convergence, but actually all types of convergent make mountains. The epic, the huge ones, the continent-wide ones, that's going to be a continental-continental convergence. That's when we're talking about the Himalayas. That's when we're talking about the Alps, okay? But the Andes, for example, are made, they're smaller than something like the Himalayas or the Alps, but they're still pretty damn big, and those are caused by an oceanic continental convergence. And you look at places like in the Aleutian Islands, and there's small mountains from an oceanic convergence. So all of these can cause wrinkling in the crust because you have squeezing together. Now, I'm going to say something that's going to blow your mind. Divergent also form mountain belts. Divergent can form mountain belts where they form low fault block mountains. And good examples of that are the Sierra Nevadas and the African Rift Valley. Okay, so what's going on there is that basically divergent is where ground pulls apart. If you have a divergent plate boundary in the middle of a continent, in other words, what we're talking about, a rifting zone, as you pull apart, chunks of the parts that you're pulling apart because it's tension, like as you pull apart, those chunks are going to spread and turn, and it's going to create these low rolling mountains associated with the divergent plate boundary. The only one of these that really can't by themselves cause a mountain belt is transform. Transform, because you have no squeezing and no pulling, you have no mountain belt forming. So mid-ocean ridges, which one goes with mid-ocean ridges? Give you a hint, it's only one plate boundary. Divergent, excellent. So we're just gonna put yes here, no, no. Trenches, which one's associated with trenches? Convergent, excellent. What kind of convergent? Oceanic, excellent. And there's one other. Oceanic, what's the other one? Look back over your notes. I know you know this. Oceanic continental, excellent, Stephen. So an oceanic continental. We don't see it with a continental convergence because continental convergence is just basically squishing the crust. There's just a big pile of crust piling and piling up as these two things squish together. And so you don't end up with that divot. You don't see trenches with divergent. Keep an eye open for that, because lots of people, that wins for like #1 wrong answer from like really good students. And the other one is transform. There's no trenches. And then which ones have earthquakes? All of them. Excellent, Stephen. Excellent, Morgan. So yes, yes, and yes. And convergent actually have the biggest and the deepest. And we'll talk about why that is in our next section on earthquakes. So this is an excellent segue to earthquakes. So earthquakes are associated with every plate boundary type, and actually use maps of earthquakes because they outline plate boundaries. So let me go ahead and grab your book for half a second. So this is an example of when I say that earthquakes outline plate boundaries. So this is a diagram. It's not going to be in the same position in your book. In your book, it's going to be in a different spot, but it's basically the same stuff as is in your book. And you can see that there's this outline of the earthquakes that's running all the way around. Like basically here, there's a line of earthquakes. Here, there's a line of earthquakes. Here, there's a line of earthquakes. These are all outlining plates. So like this is the edge of the plate of Africa. You can just basically connect the little dots of the earthquakes. You can also see these are the regions with these heavy, heavy earthquakes. These are the regions where we see a lot of convergence. So on the western edge of South America, on the eastern edge of Japan, China, and Korea, just north of Australia in Indonesia. So you can see, you can basically see how these dots can be, you can just basically connect them in order to outline the plates. Does that make sense to everyone? Yes, no, or maybe? Excellent, Kayla. Excellent, excellent, Morgan. Excellent. Excellent. Emily, thank you. Thank you for that feedback. Okay, so this is a fantastic segue into earthquakes. Okay. So let's talk a little bit about earthquakes and what they are. And if you're wondering what I'm doing, I am actually using your book to help me outline the outline, basically, so it's not jumping all over the place. So the order of my notes makes sense. So let's talk about earthquakes. And when I say earthquakes, what is an earthquake? Does anybody know? Transform when the tectonic plates collide. I didn't mean the transform. No, no worries. So when the tectonic plates collide. So Jamil, you are on the right track. They're not always caused. So earthquakes are not always caused by tectonic plates. Like for example, we sometimes get earthquakes in the Adirondacks and we're not in the plate boundary here. So earthquakes, but the vast majority of earthquakes, vast majority of our earthquakes are caused by plate boundaries. They're either slamming into each other, pulling apart, or rubbing up against each other. So an earthquake is rapid, violent shaking of the earth. And earthquakes can't be caused by humans, for example. Okay. For example, a really large, like, for example, like North Korea. When North Korea tests new nuclear devices underground, those will cause a small earthquake. They have slightly different characteristics than a naturally caused earthquake, but they're still causing an earthquake, and that's how we know that they actually did a test. So earthquakes are rapid, violent shaking of the earth. Really what they're caused by is most commonly caused by friction. In other words, the force of two things rubbing along a fault. Which is a break in the earth that shows evidence of motion. So what we're really talking about here is rubbing, okay? You have a crack in the earth where you have basically two pieces of rock, huge pieces of rock, being pushed and forced against each other, and then there's usually a sudden sort of movement in that tension, and it slides really suddenly. That sudden slide and the friction from that slide is what ultimately causes most earthquakes. Now, earthquakes can also be caused by things like cave collapses, like really small earthquakes, but almost all earthquakes are caused by some kind of friction, and that friction is almost always caused by plate boundaries in motion. So to understand a little bit better about how this actually works, it's helpful to have some words that we can use. So we're going to have, this is a cross section. I'm going to keep labeling this as a cross section. And this is not to scale. So I'm going to make a little house and a little guy. Okay, so they're standing on the surface of the earth. And what does brown represent usually in this class? What part of the earth is brown in this class? Cross, cross, cross. Excellent, Tanner. Excellent, Jamil. Excellent, Hannah. Excellent. I try wherever possible to keep iconography, in other words, the way I represent things, pretty consistent. So we're going to draw a fault. Here we have a fault. This is where we have our crack. Okay. Now, when the earthquake starts, the earthquake is not actually, like we talk about the epicenter isn't really where the earthquake is. The earthquake's point of origin is the focus. Okay. So a focus is where the earthquake originates underground. Okay. Up above that focus, that on the surface of Earth is our epicenter. So the epicenter is the point on Earth's surface above the focus. Make sense? Yes, no, yes, no, maybe? Yes, thank you, Jamil. Thank you, Jamil. These are definitions like that. So talking about two other terms, seismographs and seismograms. What is a seismograph and what is a seismogram? Or if you only know a vague definition of one of them and you're not even sure which one it is, that's okay. Just throw it on out there. Hit me with your best shot. Seismograph is a machine that measures the earthquake. Excellent, is how we measure the earthquake. Excellent, Robert. So seismographs are instruments that record the size and duration of the vibrations from an earthquake. And a seismogram is the recording taken by the seismograph. Or seismograph. Now I'm doing it. Now, if you ever get these two mixed up, as a hint, we'll go back to this when we see a sketch of a seismogram, but that M looks like the wiggles on a seismogram. So seismogram is the report it produces. Excellent, Robert. So I like that even better. So it's the report. Okay, it's basically the recording or the report. So to really understand this, you need to understand that the earthquakes are waves. Earthquakes produce waves called seismic waves. In other words, waves made by earthquakes. And there are four major types of seismic waves. P, S, L, and R. Okay, so those are the major earthquake types, or earthquake wave types, are P, S, L, and R. Now that we know what a seismograph and a seismogram are, we're going to go ahead and we're going to use these to better understand what P, S, L, and R waves actually are. So this is going to be rolling. Do you mind going back? Oh, not at all. I want to project this. No problem. So Of those four major types, these break into two subtypes, okay? So there's two subtypes of earthquake wave, or two categories, we'll say categories. Body waves and surface waves. Now, this is one of those cases where geology is super convenient, and it's exactly, thank you, it's exactly what it sounds like. It's weird. You don't have to say, please, move it, Dr. Eby. So, no, I'm not picturing that. So, body waves and surface waves. I always appreciate you letting me know because I get distracted. I'm now trying, chat is where my camera is, and it's right in front of my face. So this is what I'm trying, like, this is my attempt to give you a, like, look you in the, well, you can't even see my face. Never mind. So this is not collaborate. So body waves and surface waves. So body waves are, I was taught P wave or S wave. Is this wrong? No, that's not P or S wave is wrong. P and S wave, we're going to go back to it. They both fall under body waves. So body waves are waves that move through Earth's interior. Through Earth's body. Interior. And surface waves are waves that move along the surface. Okay. So waves that move through Earth's body and waves that move along the surface. P and S waves are body waves. They move through Earth's interior. And L and R are surface waves. Now from here on out, we're not going to worry about the difference between L and R waves. We're only going to worry about, call them surface waves, because for the purposes of this class, we just care about where they are on our seismogram. So I'm going to go ahead and I'm going to draw, well, you're going to tell me if it's a seismograph or a seismogram. Okay, and this is just an example. Okay, so we have, for example, now, first of all, is this an example? Is this a trick question? No, it's just it's checking retention. My next thing would be, is this a seismograph or a seismogram? And now Robert and Hannah are, yes, so seismogram. So this is an example seismogram. A terrible example seismogram. We won't worry about Dr. Eby just being a terrible artist, a terrible artist. So these collections of waves, and then we'll say time here, and this is just an example. So this might be 1205, and then we have 1210, and then we have 1215, like that. So this is just example. Basically, this x-axis is time. Okay. And then these waves up here, this wave over here is the P wave. This one over here is the S wave. And this over here is the surface waves. like that. It displays a minor hiccup. You mean how badly my sketch is drawn? Because all of a sudden this is at an angle, which it should not be. So we have the P wave, the S wave, and the surface waves. And later on over here, we could also have an aftershock. So in this graph, this is the time moving forward. So here we, like in your book and in most labs and that kind of stuff, it shows this is starting at time 0, and students get that mixed up. This is like literally a time on a clock. Okay, time passes in this direction. So what's happening is that the seismograph station starts at like 12, we'll say from this plot, 06, starts feeling the rumbles. And then at about 12:10, it feels the next set of rumbles. And then the next set of rumbles, okay? So P waves are called primary waves. And they travel the fastest. So they're the first on the seismogram, if we're reading from left to right, okay, which, you know, we do because we're in that part of the world where that's natural. They're also known as compression waves. Compression or pressure waves. We'll talk a little bit more about what that means in just a few seconds. I have a slinky to help. So, S waves are called secondary waves. So they're really named after where they are in the plot. So, so like S waves are called secondary waves because they're the second waves in the plot. P waves are called primary waves because they're the first, primary means first, and they're the first wave in the plot. So secondary waves travel slower. So they're the second. On the seismogram. And these are also known as shear waves. Okay, does this make sense? Yes, yes, excellent, excellent, excellent. So finally, the surface waves, these are obviously the slowest. These are the slowest waves. Now, to really understand what we mean by compression and shear, I have a tool that every earth science teacher worth their potatoes has. So we've got this here. So we're used to waves that do this, right? Up and down, back and forth, doing this sort of a thing, right? Yes, like water waves. This is hard over this short of a period, but like up and down. I wish I could see your head nodding, but I can't. Still coming to terms. Next semester, next fall. Thank you, Hannah. So pressure waves behave differently. They're actually like a squeezing that travels along the ground. Does that make sense? Okay, so shear is like this, and pressure is like this. Okay. So let's talk a little bit more about what we can use this seismogram for. You could say, where's your halite? And I appreciate you, Tanner, you, for looking back in your notes and coming up with a good GEO joke. If I had candy, I'd give you some. Well, I have candy actually, but I can't like Willy Wonka is the problem. So, and if you've never seen the Willy Wonka movie and don't get that, see the Willy Wonka movie, the original Willy Wonka movie, and you will get it. So let's go ahead and talk about how we use the seismogram. So the seismogram is used, seismograms are used with time travel graphs to determine the location and time of the earthquake. Hope a lot of them are random, so expect the unexpected. I always expect a good geology pun. I'm always hopeful. I always want to hear a good geo pun. So, this is a key idea. Move up, please. Yes, thank you, Hannah. Trying to watch the chat and the screen and this all at the same time. It's difficult, so I always appreciate that. That's actually, that reminds me of teaching in the regular classroom too, because my back is to the projector. And so very often my students are like, Dr. Eby, I have no idea what you're writing. I can't see it on the Elmo. So just let me know. Let me know when we're all good. Good to flip. Thank you, Robert. So, so how do we use a time travel graph and our data to determine the location of the earthquake? So we need that diagram. P and S time travel. Okay. So here we have these time travel curves. Okay. So this is usually referred to as a travel time graph because it's basically, I mean, it's telling you the time it takes for these different waves to travel. So basically, here's the basic idea. It's an analogy I use a lot. So understanding how to use a time travel graph and seismogram to determine the position and time of an earthquake. Okay, so understanding how to use a time travel graph and seismogram to determine the position and the time of the earthquake. So let's start off with so the basic idea. Imagine you have two people Dr. E and Usain Bolt running a race. So which one's faster? Your grade is not dependent on this answer. Who is faster? Him. Yeah, he's a hell of a lot faster. So he's really fast. And based on my performance in the virtual turkey trot this year, I am pretty damn slow. Okay. Depends on how long the race is. You've got big goals for me. I'm pretty sure, and the condition that I am post-COVID, I'm going to say the cameraman. I'm going to say the cameraman. Excellent. So one's slow and one's fast. We have two people running a race. So at the starting line, they line up together. At the halfway point, so the gun fires, but at the halfway point, or at the, we'll say at the quarter mile point, half mile point, Bolt is in the lead. And reaches the half mile point first. At 1 mile, Bolt arrives, oh, what the heck? I'm sorry, I wasn't moving around enough room. There we go. He's a sprinter, not a distance runner. Still though, Robert, I'm still gonna say this COVID butt has been teaching from a chair for way too long. I'm not gonna say that I'm gonna take on Usain Bolt. Okay, so at 1 mile, Bolt arrives long before Dr. E. So our arrival times get farther and farther apart. At greater distances. Okay, because he can run a mile or 2 miles or 3 miles way faster than I can. Once upon a time, I would say yes, when I run something like an 18-mile or a marathon, but man, that is a while ago now. So, so I'm not even going to pretend. And it makes for a bad analogy, so we're going to go with this. Okay. So you can graph in earthquakes, back to earthquakes. I am going to try to recreate the time travel graph as much as possible in our notes. Keep in mind that this is also in your book. Making sure that's not a student that just texted. So this is distance in kilometers. And this is time in minutes. Okay. And so we're going to have two curves. I'm going to try to pick two pens that are radically different in color. I'm going to go with a green pen. Will I move it up, please? Morgan, you're amazing. Thank you so much for letting me know that this is not going, you cannot see a damn thing. So we're going to do pink and green is going to be our combination. So green will be our P wave. And this curve will be our S wave. Okay, so this is what a time travel graph actually looks like. Okay, so you have a P wave and you have an S wave. Okay, and each of these lines. So, for example, we'll do this at over here. Let me get another colored. I did not leave enough room for this. Bad planning on Dr. E's part. 2,000 kilometers. And put this at 4 minutes, and over here, eight minutes. Actually, please, how well I drew a graph right off the bat. So if I go up here to this point here, and it lines up with that one over here, what this point is saying is that the P wave will be 2,000 kilometers away from the epicenter in 4 minutes. Up here, at the same point, the S wave will be 2,000 kilometers away from the epicenter in a little less than 8 minutes. Okay, so the P wave will be 2,000 kilometers away from the epicenter in about 8 minutes. So in other words, it took longer, take home message here, it took the S wave about 4 minutes longer to arrive 2,000 kilometers away. Okay, if we get even further out, let's do 4,000. At 4,000, so this would be about 7 minutes. I should have made this a whole bunch bigger. So this would be about 7 minutes, and this would be at about 13 minutes. Okay, now it's taking even more time. It's taking about almost 6 minutes as we pass through. So why do we give a crap about this, that they're arriving later than each other? Like, why do I care about the time travel graph? The time travel graph, I remember this, will we need rulers? No, not for this, because this I'm probably, so this week's lab is going to be all you draw it yourself, and there's no Pearson anything. And it's going to be kind of short, but it's going to be asked. I basically took one of my old labs and boiled it down to like 10 questions that I need to know if you're figuring this stuff out, like to have any sense of whether or not you're picking up what I'm laying down. And then next week's lab will probably be, you'll be doing this in Pearson, okay? So because they have these kinds of models and this kind of stuff that you can build off of. So it takes even longer. As you get further away, it takes longer. The time difference comes further from each other. Because you can build circumference rings based on differences and see where they interact from multiple locations to determine the center. Yes, Robert, you got this. So, but a lot of people, if some people, and I know from my experience teaching, a lot of people just had their mind blown. A lot of people have a really hard time with this S wave, P wave stuff. And so I may end up giving you a chart for P and S waves, and then you have to go back and calculate this. So the reason we care about this is that this is an idealized curve we can use to estimate it. We don't have any of this data about when it actually started until we compare it to the P and S wave time travel graph. The difference between these two is what we need. What we get out of the seismograph, or seismogram, what we get out of the seismogram, now I'm doing it, damn it. What we get out of the seismogram is the difference in arrival times between the P and S waves. Okay, so I'm going to go ahead and draw, I'm just going to freehand the box. It's bad, but it ain't that bad, and it's a hell of a lot faster. So we have a seismogram like this. Here's our P wave. Here's our S wave. Here's our surface wave. Okay. Let's suppose that this wave right here, this is our P wave. This is our S wave. So that the start of the P is at, let's say, 136. And then the start of the S wave is 140. Okay, that's what time, PM. And really in science, we use military time. I just don't want to confuse this any further. I probably should say AM then. So earthquakes do happen in the middle of the night. So as my friends in California can attest to. So we come from the start of the P wave. And here we have the start of the S wave. And we look at these two times here. Now, what's the difference in time between 1:36 and 1:40 p.m.? 4 minutes. Okay. So from that, I now look at my time travel graph over here. Let me move my new favorite mug. A student actually gave me this mug, good vibes only, and it's keeping me thriving in your absence because I miss my students. Also miss the other faculty being here. It's very weird. It's like a zombie movie sometimes around here, but that'll get better as the spring progresses. I just went in a meeting and they said more people. So what you need to do is you need to find where that gap is about 4 minutes. So in this case, if I look at this gap here is 1, 2, 3, just shy of 4. So we'd probably go from about here to about here. So maybe about 2,100 kilometers, okay? Because it's the gap in between the two that tells us what it is, okay? That tells us how far it is. So I'm just going to give the data that you need in the next little chart. I'm just going to sketch it out real fast. And I know I keep sketching things and sketching things. It is a fixed chart. No, this one in your book is highly idealized and doesn't go into small differences in the makeup of, for example, the lithosphere between different locations, which will change the P and S waves locally quite a bit. So this chart's actually very, very accurate for long distances, but if you're talking about a really small region, it's somewhat less useful, if that makes any sense. But yeah, it's a fixed chart and it's a really good estimate for this difference here. Okay, so if this is 2000, And this is we'll say 4.5 minutes, and up here it's 8.5 minutes. That's a bit of an overestimate. 2100. And I go up over here. This gap right here is about 4 minutes. So that implies that it's about 2,100 kilometers away. Does that make sense? 2,100 kilometers away, this being in kilometers. So how do they determine the time distance travels then for a location? It has to do with, they basically map the interior of the Earth using seismic waves. Both seismic waves that the Earth is generating and seismic waves that we generate. So they actually have these giant cannons where people shoot the cannon at the Earth to help understand the structures inside the Earth, which is another thing that we're going to talk about relative to earthquakes, because earthquakes can not only, like the seismogram and the information from the seismogram, can not only tell us something about how far away it is and how long ago it originated, which we'll go into in just a second. Not only how far away it is and how long ago it originated, but also tell us things about the interior structure of the Earth. And that's the last thing that I'm going to bring up today. So the P wave and the S wave, the P wave has been traveling for 4.5 minutes when it reaches this point at 1:36 p.m. So 1:36 p.m. minus about 4.5 minutes equals earthquake occurred at 1:31 and 30 seconds p.m. Does that make sense? Any other questions? 131.5, I don't know. What's a half a minute? That indicates a half a minute to me. Okay, so the lights keep turning off. This is the end of this topic. We're going to go on to how earthquakes are used to measure and map the inside of the Earth in the next topic. So we'll wait for that on Thursday. This basically gives you the foundation of what you need for lab today and for Monday people for lab on Monday. We are going to have an earthquakes lab. It'll be slightly out of sync because of the 2 weeks thing. I'm just not skipping an earthquakes lab because that's really fundamental to this course. So it's like rocks and minerals and those guys. You kind of need it. So any questions? Then why don't we say we're going to break up for today. And I hope that you have a really great afternoon. And some of you I will see at 4 o'clock. I am going to have my cell phone on me, but I'm going to go quick run and get food before lab. If you want to meet or you need to meet, let me know. I am happy to talk to you on the phone or anything like that. So those office hours are still available. I just haven't eaten all day, and I don't eat, I get mean. And nobody wants that. So same, yeah. I think that's fairly universal. So I'm going to stop the recording.